Okay, can you hear me? Can you hear me? Okay, okay. So, yeah, today we will finish the uh, explicit part of the proof, and then we will uh, go to some non-analytical part. So today we are going to treat with the remaining part of the proof to the first part of the Riemann-Roch theorem. Recall that in previously we have established the theorem. So we have proved 1, 2, and 3 for smooth and real linear Cauchy-Riemann operators. And we are going to finish the proof of the following theorem. So let sigma j, or we have associated a special volume form to be a Riemann surface, a compact Riemann surface with boundary d sigma, and we let the C and df and df star the corresponding real linear Cauchy-Riemann operators. df is a real linear Cauchy-Riemann operator, and df star is its joint operator. And we assume that they have class, they are of class W LP, where LP is greater than 2, L greater than or equal to 1, and integer. And P greater than 1, a real number. Then we know that for let R greater than 1, such that 2 over R minus 1 is bounded by K minus Q, 2 over Q, then the following holds. So this is the inequality that I forgot to mention yesterday. Yesterday we assume R is conjugate to Q. Here we assume that K is bounded by L and greater than or equal to 1, and Q is bounded by, and Q is a positive integer such that K minus 2 over Q is bounded by L minus 2 over P. So this inequality on these indices is given by considering the Sobolev embedding theorem. So the following will hold. The first one is that df and df star are Fredholm operators. And with the relation of the Fredholm index given by the index of df plus the index of df star is equal to 0. It is the first and the is 0, and the index is independent of the choice of the almost complex structure or complex structure J and K and Q, and the choice of and K and Q and the choice of D. And for the second one gives the adjoint property. That is, if eta is in LR of sigma and T01 sigma cancel with E, and we have Cauchy, and Cauchy is in the subordinate space WK-1Q sigma and with values in E, such that for all zeta lies in WKQ with boundary condition F and with values in E, tensor with T01 sigma. We have the following identity, that is the integration of eta over df per c. Integrate over the volume form of sigma is equal to the integration over sigma of the c with zeta. Now here is zeta over the volume form. Then eta has some regularity. It should belong to WKQ with boundary condition F. And here I should pick the corresponding boundary condition, that is T01 d sigma tensor with F. And we know that df star x on eta is equal to the C. And the second one is the dual result, that is, if eta is in LR sigma with values in E, and C is in the Sobolev space with values in the differential form, then such that for all zeta, which is with boundary conditions and with values in here zeta is in E, has values in E. So here zeta has values in the differential form. We have the integration over sigma of the pairing eta with here the pairing of df star of zeta and eta over integration over sigma is equal to integration of zeta and C over the volume form. Then we will have eta is in fact is in WKQ with boundary conditions, and we have the C is in W, and we have dfx on eta is the C. So we have proved the theorem in the case when df is smooth real linear Cauchy-Riemann operator. And now we are concerning the case when df is non-smooth, it is only of class LP. So in order to achieve this, we need a lemma. The lemma states that states when the case states in what cases the superleft space LR and the superleft space LR and WK minus 1Q or WKQ can be regarded as the the lemma states that in what cases the two elements in a given superleft in two given superleft spaces can have a pairing. So the first one is that if we assume F is greater than 1 and is the conjugate of R and is conjugate to R. This means that 1 over S plus 1 over R is 1. Then we have the embedding WK minus 1Q can embed into LS, and hence we have LR can be embedded into WK minus 1, the dual of WK minus 1Q. For the second one is that in any cases we have WKQ can be embedded into the dual of WK minus 1Q. And the last statement is that if we have the inequality minus 1 over 2 is bounded by, or to say it is sufficient and necessary condition, that is minus 1 over 2 is bounded by k minus q 2 over q, then we will have the here with L minus 1. So this is independent of the choice of K and L. Assume that K is bounded by L and P and Q satisfies the given inequality. But when we consider WK minus 1Q, WKQ embedded into WK minus the dual of WK minus 1Q, then we need the condition that minus 2 over 1 is bounded by K minus 2 over Q. So the proof is just given by using the superleft embedding theorem. And so in order to see one, we need to show that WK minus 1Q is embedded in LS, and if KQ is greater than 2, there is nothing to prove. Greater than or equal to 2, there is nothing to prove. Because we know that in any cases, when we have F is in WK minus 1Q, so here is K minus 1Q. So, and with product of index greater than 2, then this tells us that because we are concerning functions on the Riemann surface, so the index is 2. So this tells us that F is either continuous or it is LP for all P, and this implies that F is in LS. And here this implies that F times any function G with G belongs to LS, and if LS norm is bounded by the L infinity norm of F times the LS norm of G. So it is again finite. So this tells us that in any cases, if we have K minus 1Q times Q is greater than or equal to 2, then we will then the embedding is obvious. No, here with R, we need the embedding into LS, so here is R. Yes. So now we consider the case when K minus 1 times Q is bounded by 2. It's less than 2, and this implies that K minus 2 over Q is less than is less than 1. Well, we have the relation of R, that is, we have this relation. So this tells us that R over 2 minus 1 is bounded by K minus 2 over Q. We have K minus 1 is less than 1, so this implies that no, what I'm going to say is that yes, if this is bounded by 2, then yeah. So we have the embedding K WK minus 1Q is included in LT for any T greater than or equal to Q, and bounded by the uh, and bounded by so we apply the overlap embedding theorem. So this is 2 minus K minus 1 times Q, and here is 2Q. So we know that this is equal to 2 and 2 over Q minus K minus 1. And we know that we have the relation R minus 2 over R minus 1 is bounded by K minus Q over 2 over Q. So we have minus, no, here is minus 1. So we have 1 minus 2 over R is greater than or equal to 2 over Q minus K. So we have, no, since we have 2 over R minus 1 is bounded by, okay. So we have 2 minus 2 over R minus 1 is bounded by K minus 2 over Q. So we will have R is bounded by 2 times K minus 2 over Q minus 1 over, so this is KQ minus 2 plus 1. And yeah, okay. Yeah. So what we are going to see is that we want to show that WK minus 1Q is embedded into LS. And we know that S is the conjugate to R, so we have S equals to S minus 1, R minus 1 over R. Yeah. So if we want to see that this is embedded into S, then by the Sobolev embedding by the Holder's inequality and the compactness, this amounts to say that the Holder inequality, so this amounts to say that we only need to see that S is bounded by T. S is bounded by this inequality, by this amount. Then we will have a given embedding because of the compactness. So the measure of the whole Riemann surface is finite. Then we just apply the Holder inequality. So in order to see this, we say that this is equivalent to saying that R minus 1 over R minus 1 is bounded by 2 over 2 over Q minus K minus 1. So when we do some calculation, we will have it's bounded by 2R minus 2. So So we will have no, this is 3. Uh, 1 minute. Yes, this is 1. This is 2. So, and this is equivalent to saying that minus k minus 3 times r is bounded by minus 2, and no, I think there is so yes, and we know that s over 2 plus r over 2 is equal to 2, and we have the inequality out of 2 minus 1 is bounded by k minus q over 2 over q. So we have we replace this term by 2 minus s over 2 minus 1 is bounded. So we have 1 minus s over 2 is bounded by k minus q over 2. So this tells us that s over 2 is greater than or equal to k 1 minus k plus q over 2. And this tells us that 2 over s is bounded by the 2 minus kq plus q. That is 2 minus k minus 1q over 1. So this tells us that we have the, yes, this tells us that S is bounded by this. So so we have the embedding wk minus 1q is embedded into Ls. And which if when we take a dual, we obtain a dual mass Lr to wk minus 1, the dual of wk minus 1q, and they are and it is a map of Banach spaces. And we know that the embedding is dense because we always have the smooth function embedded into the superlap space, and it is dense in Ls. So the superlap space is also dense in Ls, and this tells us that this is an embedding. So finally, we obtain Lr can be embedded into the dual of wk minus 1q. That is, we have the pairing eta and df of C. Df of zeta is well defined. The integration is well defined. So this tells us this. And for second one, we know that if we want to say that WKQ is embedded into the dual of WL minus 1P, it suffices to see that W of L minus 1P into the it suffices to see that so WKQ can be embedded into some LP space, and this LP space can be embedded into WL minus 1P star. So in the case when KQ is greater or equal than 2, there is nothing to say. So we are considering the case when KQ is less than or equal to 2. And in this case, we must have K equals to 1 and Q is bounded by 2, and Q is less than 2. So we want to establish an embedding first for LP into the dual of L minus 1, WL minus 1P, and we know that LP is greater than 2. And if L minus 1P is also greater than 2, then there is nothing to prove. Because then they embed into the space of continuous functions, and all these things can naturally embed it into the dual of the continuous function. So we assume that L minus 1P is also bounded by 2. This is equivalent to saying that L minus P 2 over P is bounded by 1. So we again apply the, so we know that when we have, so we have the probability embedding WL minus 1P is embedded into LT for T greater than T and bounded by the 2 minus L minus 1P over 2P. So the surface, so we have the embedding, this is some T. So we have the embedding Ls is embedded into WL minus 1P. If and only if we have Ls if S is bounded by the number 2P over 2 minus L minus 1P. So it suffices for us to check if, so we have WKQ must embedded into 2 minus KQ of 2Q. So it suffices to check if 2Q over, no. So I think the smallest one is LQ. No, I think yes, embedded into 2 minus KQ. So it suffices to check if we have the L. So if we have 2Q over 2 minus KQ is bounded by 2P over L plus 1P minus 2. Yes, so yes, here T is bounded by this, but we are considering the dual of T. So so the dual of T will be given by again 2P but over L plus 1P minus 2. So this is, we take the T over 1 and minus, so we take the fractional T minus 1 over T. So but by that direct checking, we have this is equivalent to saying that 2 over Q minus K is bounded by L plus 1 minus P over 2. But we know that this is obvious the case because we have so yes. Yes, we know that this is obvious the case because it is easy to check that this is the case. So we have the embedding. And when we can embed into this, then the second, then this will embed it into the dual of L minus 1P, the dual of L minus 1P. And for the last one, we know that it suffices for us to check the case when KQ is bounded by 2, because other cases will be trivial. So we have, in this case, we have K is equal to 1 and Q is bounded by 2. So we are considering the thing when W1Q is embedded into the dual of LQ, which is L Q minus 1 over Q. But we know that W1Q can be embedded into L over 2 minus Q over 2Q. So it's something to try that if it can be further embedded into 2 minus 1 over Q. So this suffices to check that 2Q over 2 minus Q is bounded by Q over Q minus 1. This is equivalent to saying that. And this and we just have Q is bounded by 1. Uh, no, no, it's equivalent to saying that uh, 2Q minus 2 is bounded by Q 2 minus Q, so Q is yeah. So this amounts to say that Q over 2 is Q over 2, yes, minus 1 is bounded by 2 minus 2 over 2. So this is equivalent to saying that Q over 2 uh, minus 1 is greater than or equal to uh, minus of 2 over 1. Um, no, there is something wrong. Okay, so let's try again. Yes, this is when we take the dual is 2 minus 2 of 2q is bounded by q minus q1 is equal to 1 minus q of 1, and this is equal to q1 minus 2 of 1. So this amount to say that minus 2 of 1 is bounded by 1 minus 2 over q. So and we have k equals 1, so this is k minus 2 over q. And in other cases, that is if kq is greater than or equal to 2, the condition is obvious because this is just q over kq minus 2. So this is our sufficient and necessary condition. So the last statement is vital in our treatment of non-smooth operators. And now we begin the proof in the case D and df and df star is of class WKP, WLP. So in this case, we have the recall that we have the following proposition that when A is of class WL minus 1P of sigma with values in the endomorphism, tensor with some one form, then we will have A is a compact operator. From the space WKQ with boundary F of sigma and E to WK minus 1Q of the space sigma with values in T01 sigma tensor with E. This is proved before, so we know that in this case, any df is equal to some other df which is smooth and plus a non-smooth zero order operator A. So we know that they differ by an non-smooth but compact operator. So we know that the Fredholm index of df and df star and so we know that because they differ by compare operator, we know that their Fredholm index is the same. Similarly, we have the result for the dual operator. But it is not enough. We only see that the Fredholm index of them is the same, but we don't know what the kernel and co-kernel of them is looks like. So we still need to check the second and the first statement. So in this case, we need to so in this case, we need to consider the so now we assume that we have the embedding that is minus 201 is bounded by k minus 2 over q. So we have all the embedding results in the lemma. So the one so we have all these embedding results, and this tells us that when we have this tells us that we can naturally do the integration. So we need to check that how to say this. So yeah, we need to establish the decomposition. That is k minus 1 of q with values of differential form will be isomorphic to the kernel of df star direct sum with the image of df. And in order to achieve this, so we need to see that so yes, so we have the elliptic estimate still holds because we have the but only in a case we can. But in this case, we can only to see that if eta is belongs to the kernel of df star, then we must have eta is only of class L minus 1p. No, it's only of class WLP with boundary conditions. But we still have the natural embedding into k minus 1q. So we still have this kernel of df star as the subspace of k minus 1q. And since we have it is of class WKPQ, we have eta. So we have the kernel of df star can be naturally embedded into the co-kernel of df. No, it is only a map. It is not we have not proved that it is an inclusion, but it is easy to see that it is an inclusion because we know that if eta, if you pair it with eta and df per c, in a smooth case, when we integrate over sigma, we will obtain in a smooth case. And we will obtain that it is equal to df star of eta and pairing with the c. Here we have the boundary condition. So, but in this case, the boundary condition cancelled. So we have kernel of df star is mapped into the co-kernel of df. And why it is an inclusion? Because we know that So so why it is an inclusion? Yeah. And also naturally we similarly we have the kernel of df is naturally mapped into the co-kernel of df star. Yeah, we know that it is an inclusion because of the obvious reason that when this integration is zero for all the c. No, this is obvious zero. So with the obvious reason that if eta pairing with any f to c equals to eta 2 pairing with any df to c for all sigma, no. So why it is yes, because it is just yes, because this can factor through the space WK minus 1Q, and this is an inclusion. No, I mean yes, yeah, this is an inclusion, so this should be an inclusion. But we know, but we need to say that it is an isomorphism. So we consider the direct sum. Kernel df mapped into the kernel of df direct sum with kernel of df star, so kernel of df star. So this is the general inclusion. And when we compute the index, we know that the index of kernel of df plus the index of kernel of df star. It is related to the Fredholm index, and we know that it is the Fredholm index of df plus the Fredholm index of df star, and minus the dimension plus the dimension of cokernel of df plus the dimension of the cokernel of df star. So we know that they cancel because they are related to some smooth Cauchy-Riemann operators, and in this case we have the same, the smooth Cauchy-Riemann operator, the dual of the smooth, the adjoint of the smooth Cauchy-Riemann operator plus the adjoint of A. So this tells us that their dimensions are the same and it's an inclusion. So this tells us that this, if we have f and g, this is f direct sum of g. The f direct sum of g is an isomorphism. So this tells us that both f and g are isomorphisms. So this tells us that the kernel of df is isomorphic to the co-kernel of df star, and also for the adjoint result that the kernel of df star is isomorphic to the co-kernel of df. So we have the decomposition. And with this decomposition, then for any eta belongs to LR of sigma and with values in E, cancel with the 0, 1 form, we have so we and so what I'm going to do, yes. So eta is in LR and C is in W of K minus 1Q with values in E. Then we have the C can be decomposed because we have the decomposition for WK minus 1Q, so we have the C can be decomposed as eta eta 0 plus df times C0, where C0 must lie in WKQF of sigma with values in no, it's yes, it must be KDF star because yeah, with values in T0 1 sigma times over D. So so if eta satisfies the L2 norm pair with any zeta is equal to the pairing of C with this, then we decompose C into eta 0 plus the CF star of C0 and pairing with zeta, CF zeta. Uh, no, this is zeta. No, okay, so this is zeta. And I think this should be here. So we have the composition of WK minus 1Q of E. So it is the C0 plus eta 0. And eta is with values in this. So this is eta 0. And this is the C0. So we know that the C0 belongs to WK minus 1Q and with values in E. And we know that zeta is belongs to K of yeah, no. Because C0 belongs to the kernel of df, so we know that C0 is in fact that in WKQ. So this tells us that it is in WKQ, and zeta is also in WKQ. And we know that eta 0 is belongs to this, so this will equal to eta 0 and df zeta L2. And when we pick no, what was to say? Yes, when we pick uh, yeah, when we pick zeta equals to the C0, we will obtain that then we have the norm of the C0 squared is equal to eta minus eta 0 pairing with df to C0. That's the also norm of this. So this tells us that, but this is 0. So this tells us that the C0 is 0. And we again go back to this. This will tell us that eta minus eta 0 pairing with the image of zeta of the L2 norm is always 0 for any zeta. So this tells us that eta minus zeta 0 must belong to the kernel of df star. No, the co-kernel of df. Yeah. So the co-kernel of df, but it is isomorphic to kernel of df star. So eta is smooth. So eta is has some regularity, must belong to LKP, WLP, and we know that eta df star eta is 0. But we again need the boundary conditions, but it is obvious because yes, because eta 0 is also belongs to the eta 0 also belongs to the WKQ of F with or LP of F with values in this cancel with 0, 1 sigma. So this gives this proves 2, and 3 is completely similar, and 3 is completely similar. But note that here we use the fact that we must embed wk minus 1q into the dual of k. Yes, we use the fact that we must embed wkq into the dual of wk minus 1q. So that the what going to say? Uh, yes, here we must impose the fact that the wkq can be included into. Yes, we must use this. WKQ can be embedded into a dual of WK minus 1Q. So, so we can naturally do the pairing and obtain the result. But we again need to uh, drop this condition, that is 2 and 3 holds in fact in general cases, in any cases. That is, we do not need the condition, but in this case, we do not have the embedding of WKQ into the dual of WK minus 1Q, but we only need to show the decomposition. Sigma E is isomorphic to the kernel of BF direct sum with the with the image of BF star. So we only need this decomposition, and similarly for WK minus 1Q of some of decomposition as the kernel of BF star direct sum with the image of BF. But note that we have the embedding WLP embedded into WK minus 1, the dual of WK minus 1Q. So we have the natural inclusion of the kernel of BF into the WLP, and then into the dual of WK minus 1Q. So we again have the fact that the kernel of BF can be embedded into the co-kernel of BF star. No, the co-kernel. Yes, the co-kernel of BF star. And with the same procedure, we will obtain that the kernel of BF is in fact isomorphic to the co-kernel of BF star. So we have the decomposition. And with this decomposition, we then easy to verify that the decomposition will give us the statement 2 and 3. So so the generalized so we recall that for the generalized Riemann-Roch theorem, we only need to impose that when the integration of when the integration over the I think yes, the generalized Riemann-Roch theorem only says that a pairing with eta and df zeta no yes. So and then we have the proof, the generalized Riemann-Roch theorem, the first part. I think we have also got the explicit statement of the proof of the theorem. So let's remind let's record the main theorem. So yeah. So this says that TF and DF star are Fredholm. This has been proved. And we have the following relation. If eta and the kernels are independent of both K and Q, and this is obvious because the kernels has the maximal regularity, that is, it will belong to WLP, so it is independent of K and Q. And we have, moreover, we have the following. So eta belongs to the image of DF if and only if the integration over sigma of eta pairing with eta 0 over the volume form is 0 for any eta 0 belongs to wk minus 1q sigma and t01 sigma times over G. So no, it is eta 0 belongs to the kernel of df star. Yeah. So we know that when eta 0 is in the kernel of df star, then we have, in fact, we have eta belongs to the image of df, then eta is df C for some df zeta for some zeta, and then this tells us that the integration of d of eta, that is df zeta, and pairing with eta 0 is equal to the integration of zeta and df eta 0. So it is 0. So this is equivalent to saying that eta pairing with any eta 0 and integrated over the sigma is 0. And here, and there is another dual result. If eta is in the df star, this is equivalent to saying that the integration of over sigma of eta pairing with eta 0 is 0 for any eta 0 belongs to the kernel of df. So the proofs are almost the same. So the generalized Riemann-Roch theorem follows easily from this argument. We still need to check another two cases. The second one is the formula that the index of df is equal to n times the over characteristic of sigma plus the boundary Maslow index. I think there should be some. Yes, there is nothing left here. And also we have and we should have the boundary Maslow index is equal to the second term, the twice of the first term class when boundary is empty. And still need to check the codirel embedding. That is when we have degree is when we have the boundary Maslow index is sufficiently small. If it is less than 0, then we should have the surjectivity, injectivity of df is injective. Yeah, df injective. And when it is sufficiently large, explicitly it is said that the boundary Maslow plus 2 times pi e is greater than 0. here E is a line bundle, so it's of dimension 2. When mu EF is greater than plus 2 of the characteristics of sigma is greater than 0, then EF is surjective. That is, it has no cokernels. So in order to do this, we should introduce the master of index. I think today we can stop a little earlier because we have done the first part of the proof, and the last and the remaining terms are not quite hard. So are there any questions to the remaining to today's talk? So where is my